All right, welcome everyone to today's live science session. And the agenda for today is quantum example teardowns. So we're going to focus in very intensely on a specific quantum mechanics example, quantum information, something quantum, and look at it in detail and try to use that one example to see how deep we can get to actually understanding it and potentially visually or digitally recreating it. So leveraging the quantum framework, leveraging the examples we have, and then trying to see if we can find a correspondence to the Wolfram Physics project as well. That would be quite cool. So thanks for joining us, Nick. Maybe you'd like to just start by giving us a brief intro of what you wanted to address today. What is the agenda?
Well, it would be easier to just start sharing what do I have.
Okay, let's jump into it.
Because I want to go through this CHSH game, and which is like the extension of Bell inequality, but formulated pretty neatly in our framework. And I wrote like a whole blog post about it and all the diagrammatic notations in the framework and how we can approach the specific game, and like with a bunch of multi-way systems, diagrams, memes, and all that, right? So, and now I just want to go through it because since last time I looked into this problem, I got some new ideas and potentially some different interpretations of quantum stuff, essentially. Like how can you interpret those problematic statements that you get when you deal with this setups like this, typical setups that you get from Bell inequalities. So first I want to just remind everyone what is this game is all about, what is the set.
Can we zoom in maybe an extra half of this?
Always forget.
There we go.
Sure.
Cool. Okay, let's. So what is the game? Yeah, what is actually?
So the setup is. Yeah, so you, as usual, you have some kind of parties. There are 3 parties in this game involved: Alice and Bob and Charlie, right? So Charlie is some kind of referee, which monitors the game. So he also acts as some kind of random generator, essentially. He's not very important. So in this diagram, is represented as like 2 random coins that go to Alice and Bob, right? So you just think of Alice and Bob awaiting some input from Charlie, and they want to do some kind of experiments and output some answer based on the input from Charlie, and potentially some prepared, basically some preparation that Alice and Bob can do before the game starts. And the condition for winning this game, this is the condition. It looks quite involved, but if you think of it, what it actually means in English, it says basically if X and Y are the Charlie outputs, like X is the first coin that goes to Alice part, Y is the coin outcome that goes to the Bob part, and A, B is just the answers Alice and Bob provide, right? And the condition for winning at this game for Alice and Bob is essentially reads like this: they should output the same answer whenever Charlie beats contains at least 1 tails or something, or heads, right? So there are 2 coins. If either of them it's like a 0 or tails or whatever heads, then Alice and Bob should output the same answer. Otherwise, they should output different answers. That's how you can read it.
Okay.
Kind of somewhat pretty involved condition, but you can just compute the result, whatever. If you just collect a bunch of experiments like that, when Alice and Bob produces an answer, and then compute how many times they win, you essentially can compute a number for the winning probability or the winning rate for this game.
Okay, so it's a game of chance where you're trying to beat the odds of figuring out what somebody far away from you has. So Alice and Bob are separated in space-time, or they're separated in locality, and the higher your probability of figuring out kind of what the other person has based on what you have, that increases your winning odds. Is that like one way to summarize it?
Yeah. Basically, Alice and Bob are not allowed to communicate. Maybe after the Charlie starts generating his random numbers, Alice and Bob can prepare some maybe common book of answers that they can address and maybe correlate their answers
That's allowed.
How classically, right? That's allowed, but still the maximum percentage of maximum winning rate that they can achieve classically, you can prove it, it's like 75%. Okay, and this particular example I can code it using quantum variant of this game, when Alice and Bob, instead of sharing some common book with prepared random numbers that they can share, right? They actually have entanglement pair, like a bell pair shared between them. They can, so that it's correlated and they can measure it together. And based on the result of the measurement, they can base their answer. They can base their answer on the result of the measurement of that pair.
So typically this would be explained as like a quantum entangled particle pair or some kind of like entangled state that they can both measure independently.
Yeah, exactly. They can, like, there's maybe some device that prepares this entangled pair and sends two particles to Alice, another one to Alice, another one to Bob. They do some quantum experiment on their parts, write the result in their textbook or in some like notebook or something, right? Then do it multiple times, and then they join together and compare the results and how many times they actually won, right? And classically, you can show that they can do better than 75%.
Playing an optimal strategy. So it's a bit of game theory here, saying based on optimal strategy, that's the maximum percentage you could get.
Yeah. But what quantum theory tells us that they can do exactly this kind of experiment with all the quantum gates explicitly laid out and what they measure and all that, right? You can achieve more than 85% of winning at this game. Like, this is the exact probability distribution that they can get after they deploy this strategy on the random inputs that Charlie provides them, right? And so that's what we're gonna do today, trying to tear down this experiment, like to its essential components, understand what is actually happening, right? And we're gonna do it in some unconventional way.
Okay.
Right? Well, first of all, you should, obviously you can like just take this circuit and run it. You get this quantum measurement which contains all the probabilities, right? I wrote this little helper function which is going to be included in the notebook. I'm going to share it at the end of this live stream. You just test this list of probabilities. It's going to be like exact. Maybe you can simplify it, right? But its numerical values looks like this, which is exactly the bar chart you see in that little summary box over there. Right. So basically that's the target joint probability distribution that we want to achieve for these four outcomes, A, X, Y, and B, right? So we have four targets that we measured, and that's the joint distribution of those four random binary variables, right? So it's like head or tails, yes, no, up, down, 0, 1, all those different kind of outcomes that you can consider. Okay, so the way we're gonna do it, we're gonna perform some series of simplification steps on this circuit first. Like the first simplification, you can do it directly on this circuit. You basically can compact all of the Alice bits, like their like controlled measurements, whatever they do, the controlled gates measurements, even the Charlie bits, you can just collapse into some single box that Alice does. And that's actually what actual experiments do. Like I've seen the last experiment, like 2015, maybe they actually have some quantum random generators instead of Charlie throwing coins, of course, because they have to perform it very quickly, maybe like in two different labs separated 13 kilometers away from each other, right? So they actually have some setups like this. So we're gonna simplify this. We just into three components where we still have this bell pair, an entanglement pair shared between Alice and Bob. And now just the whole setup of both of the apparatus measurement devices are just compressed into a single box for Alice and Bob, right? We can so this is like a simple CHSH, and probability list again produces the same kind of distribution that we want, and we can check that it's exactly the same winning probability, and you can also compute the CHSH factor, which is like a Bell factor. Very famously, it also classically can't reach more than 2 in this case, right? So it's like a Serlson bound. So it's not like a Serlson bound. Classically, it can be more than 2, but this, if you compute it for this particular setup, you get something again non-classical, which violates the Bell inequality or CHSH inequality in this case, right? So the next simplification is a little bit more involved. We're actually gonna transform it in a way. Let me show the wires, dimensions on the wires. Okay, so while before we had this two-dimensional wires, which naturally were corresponding to qubits are two-dimensional quantum states, we essentially want to convert this circuit to phase space, right? We chose some particular basis. You don't have to worry which basis it is. It's like this natural basis that all the qubits look like they're like two dimensional. Like I can show the example. Like for example, for a random quantum state like rho, right? Mm-hmm. If you transform it to a phase space, what you get is just a list of numbers or quasi-probabilities, mm-hmm. like this, right? Which like with two indices. Let's use this one. It's the same one that we can use, right? So now in this particular basis, those indices have a very specific meaning. Like the first one is corresponding to essentially the qubit version of a momentum, and the second one corresponds to a qubit version of position.
Sure.
So it's like a quantum version of the phase space, right? But instead of like position, momentum and position, you can think of it as two different spin orientations, or spin and phase, or whatever, right? So the point is that if you sum up, if you look at it as a matrix like this, mm-hmm. Not like this, maybe. Yeah, I need to reshape it. Actually, I think I have a property that does exactly this. I call it prime quasi-probability. Okay, so it's like a matrix like this. It contains the same numbers, as you can mm-hmm. see. And if you marginalize all these probabilities, this is like a joint probability table. Mm-hmm. If you sum over rows, you'll get exactly the probabilities of measuring this particular state in like a computational basis or a Z basis. If you sum over columns instead, you get the probabilities of measuring the same state in X basis, which corresponds to momentum.
Interesting.
Right?
Okay.
So essentially, these numbers encode the complete information about the state. Right? You can recover all the elements of its density matrix or state vector just from the quasi probabilities. Well, here we got lucky actually. There are none of those probabilities are negative. Let's get a different one. Right? So sometimes they're negative. So it's not it's not a classical joint distribution. Sometimes some probabilities are negative, but you still recover this marginal property. If you sum over rows or columns, you get the actual probabilities that sum up to 1 and positive.
When you say it's not classical, I mean, it still adds up to 1, right? So I guess, does classical mean that the components...
If you sum all of them...
Yeah.
But it's not classical because they have negative probabilities. Like a joint distribution over Z and X basis measurement contain negative probabilities. So we can interpret them as actually measuring. So there's some correlation between those, momentum and coordinate, essentially, that you have to encode. But there's some different basis that guarantees you to get always the positive probabilities. right? So in a way, but we're gonna use this one because we're still gonna read of those negative probabilities in a different way. But at least this basis has this nice properties of this marginalizing it and getting the more common, more known probabilities, like of measuring this particular qubit in this or that basis.
It's also the fact that you could have greater than one probability that makes it non-classical, right? Together with negative, you now also have greater than one.
Yeah, it's also possible. Maybe we can try like generating a few random ones. Maybe we're gonna hit one. Though I'm not sure.
Because always going to be divided by 2, so it'll be quite rare to get a single probability that's greater than 1.
Yeah, it's possible. Well, it's more likely when you have probabilities of actual transition between states, like applying the operators and gates on the states. Those essentially are matrices instead of these vectors, like this. They show you how those probabilities transition from one to another. Those, I think, more likely to get to be more than 1 or less than 0, right? So you can naturally like transform, I don't know, a Hadamard gate or C0 to the same kind of basis, and you see there's gonna be minus half about t. That's pretty large. I don't know, maybe like basic gates don't even have greater than 1 probabilities. Maybe it's just a fact, which I don't know how to prove, but maybe it is. But anyway, so that's what we're gonna do. It's just gonna transform every gate and this single state they prepare, the entanglement pair between Alice and Bob. We're gonna transform it into this phase-space representation, so that in this way we're gonna get rid of all the complex numbers. So in the way, because in this original form it contains some rotation, which is like a complex. Let's see what this particular gate is doing. It rotates around y-axis by this pi/4 angle. Maybe it's not even. Maybe it doesn't even contain a complex number, so it's maybe pointless to do so anyway. But whatever.
So is that part of the original experiment? You have to do some kind of transformation on one of the entangled pair to limit the results of what gets revealed. Is there something like that? Like it's passed through a polarizer or something like that? Is that part of the original experiment to make this work?
I didn't get which exactly. The use of polarizer or what?
Yeah, so in some of the quantum experiments, you kind of you affect the one quantum the entangled particle, and you don't affect the other one. Kind of just as maybe just as extra certainty that that it is the entanglement causing the probability to be above 75%. I remember reading something like that. It was just like extra verification, I guess.
Maybe the actual this Bell inequality violating setup is not unique. I imagine like Alice doing something like different, maybe doing nothing at all, and Bob making something more complicated, but you still can violate your Bell inequality anyway, right? But this is, I think, more conventional setup that you can find in the literature.
Yeah.
It's just like they condition on the corresponding bits to something like perform some Hadamard gate, which like turns like just changes basis from X to Z and back. And Bob is just doing some rotation, and you can see how the probabilities change based on this angle, for example. You can also explore it. But, okay, so let's continue. So we convert it to the phase space. Also, if you notice that there's like a number of dimensions, essentially squared. So if the qubit has 2 complex dimensions to encode its amplitudes, in phase space you have to have 4 real numbers to encode its quasi-distribution. So that's why like the dimensions of these wires are squared. Before we had 2, now there are 4-dimensional wires, and we're also adding this special measurement spiders at the end, so that we essentially show the decoherence explicitly. So it's this measurement, it's like reduces the dimension. You see that the wire thickness changes, so it becomes thinner. That's why it's like turns from 4-dimensional distribution to the 2-dimensional distribution. And also we combine them back into a single system. And that's the thing we're gonna again combine. We can check this first. We can like check the display space. Now again reproduces the same variant probabilities, but now the difference is that before we looked at the probability list, because it's like you have to conventionally extract the amplitudes, square them, right? And that's how you recover the probabilities using the Born rule. But in phase space, the amplitudes or the state vectors, the distributions, probabilities are already probabilities, right? So we don't have to do any squaring. So the same probability distribution is basically recovered from the phase space, just from the amplitudes. So that's why we use the amplitudes here. And then we just do this like combining like all the measurement and just and combining them into a single wire at the end, just reducing this whole setup into the simplest possible form, right? So I guess we can also show the wire dimensions. It's gonna be, no, it's not the simplest. Now we're gonna a little bit make it more difficult from this point. From this point, now we're gonna make it more difficult than simple. So this is like a phase space, the simplest phase space setup that CHSH game can be reduced to, right? And if you notice, you can just extract all the list of operators, which is just free. One corresponds to the Bell state, right? We just with 2 outputs, and 2 corresponding to Alice and Bob, which just have some input and output, right? Which are matrices. And if you extract those matrices and sum the rows or columns, you see that they all sum up to 1. So those matrices and vectors essentially behave like distributions or conditional tables, conditional probability tables, right? So, but not quite, because they are not actual probability tables, but quasi-probability tables. So if you actually look at those tables, they're still gonna contain negative numbers, right? Like this.
Okay.
Right. So those are quasi-probability quasi-probabilities or conditional quasi-probabilities for Alice and Bob.
Is there anything to the shape of the quantum operator on the right-hand side there where it's like red all around a blue center, or was that just a random, did it randomly come to that picture? On the right,
do you mean
up just about that, the quantum operator, yes, that pure map.
I don't know. It's just how it turned out to be. It's like a signature for the matrix. Okay. Right? Just plotting the amplitudes. So I don't know, it just turns out this way.
Okay.
Anyway, so as this now contained negative probabilities and it can be interpreted quasi-probabilistically, we can get rid of those quasi-probabilities with another trick, right? We're gonna positivize this setup now. And this we're gonna do by introducing like a special, I'm gonna show the 5 dimensions now again. The way we're gonna do it by introducing like the special variables. Essentially, if before our outcomes were 4-dimensional, essentially we had 4 possible outcomes that Alice and Bob can produce combined, because they also have this random bit that Charlie generated. We want to double this amount, essentially encoding all possible negative outcomes as a separate outcome.
Okay.
Or negative probabilities as a separate outcome that explicitly has this negative sign encoded in it, right? That's basically what this function is doing here. I also normalize it manually so that, again, like if you recover all these 8-dimensional matrices and vectors now, you still get the nice summation to 1, so that it behaves as conditional probability tables and probability distributions. But now if you look at the matrix forms, like this one, it also do it numerically, it's just going to contain positive numbers. Okay, of course, it increases in size because they're now 8 by 8, but now it's like where you start with the normal probability distribution, you perform some stochastic process on one part of it and another stochastic process on another part of it, and you recover some final distribution over this doubled set of variables that contain explicitly positive outcomes and negative outcomes. Okay.
So how exactly do the negatives disappear like that? Is it just an algebraic reality based on increasing the size and then multiplying it by that's like a random stochastic value?
Let's try some example. It's like we generated a random state there before, right? I think I've implemented a bunch of properties that actually shows us explicitly how this arbitrary state can look like in this doubled positive basis. How did I put it? Like sector chart? Okay, yes. It's like a nice visualization when you just go through this process of turning your quantum state into phase space using quasi-probabilities and then doubling your dimension again in order to encode your negative outcomes explicitly, right? You can now like show the whole amplitudes as the sector chart with positive and negative explicitly. Now it's like gonna contain some basically 4 outer sectors are now correspond to positive probabilities, and 4 negative sectors correspond to negative outcomes and negative probabilities, right? So let's just try some different state. Maybe try random mixed, right? So they just gonna all contain. So this is like some positive numbers, but we explicitly tell, okay, this was technically a negative probability, but we just show it, okay, as this is actually some component to this state as a negative outcome with this particular amplitude, and you can renormalize it to get the probability distribution over this double space of outcomes.
Okay.
And if you do it like this, actually, if you just run it, try numerical first. You're gonna see those amplitudes explicitly for all possible sectors for Alice and Bob combined answers. So, because they answer in sectors now that both can be either positive or negative, you can see all the positive, like maybe I chopped those. There's some numerical errors like here, but they all should be just positive numbers. So basically have probabilities of, now we have like a joint probability distribution over this positive and negative outcomes. But it is just no longer a quasi distribution or anything like that. It's purely classical distribution, but you essentially shoved all the weirdness of quantum mechanics of quantum theory of negative probabilities into explicit states that we just describe as some kind of negative outcomes.
Okay.
Right?
Okay.
Essentially, yeah.
So what happens in this situation with greater than 1 probabilities? Does it just get resolved as well automatically based on?
They're also going to be resolved here because you renormalize after you introduce this extra negative outcome. You can renormalize your state.
Okay.
Right, and now it's like just a normal distribution that sums up to 1 with positive only probabilities.
Got it.
Right, so we basically delayed all the problems of quantum theory till the very end. Right, it's like a start with a new distribution, apply something, you get a new distribution over this positive and negative outcomes at the end. Right, but how you recover? Now you ask yourself how you would recover the actual distribution that you measure, because you don't measure the negative outcomes in any way. It doesn't make sense, right?
Makes sense. I mean, it makes sense to do it this way.
Yeah. Right. So we delayed it. Well, you can also show how it evolves, right? So it's just you can show kind of multi-way system which contains only positive probabilities.
Is there any way just visually to make those little circles, those actual little shapes?
No, I tried, but it looked too crowded.
Okay.
So it's already too involved. Just two tip is fine, right?
It's pretty cool.
Just enough to understand there's like each edge corresponds to a positive probability of transitioning from this state to other state, and this is your final joint distribution over these states.
So is it 16 in the first row and then double again? What are we looking at here in terms of numbers?
It's 16, yes, but then it's like this matrix here, it contains 8 by 8, right? And it only you essentially apply it in some particular order, like Alice first, Bob second, or other way around. When you apply Alice to this original branched layer of the multivariate system in 16 different states, you apply a single matrix. It's gonna branch like each of the. It's just gonna produce two outcomes. But this is, I think, because
there's also merging. There's also merging happening there, right? There's branching and merging. Because I see some of those arrows are.
Oh yeah, you can describe it. Merging is basically because there's some equivalence. They're actually the same state. You can see explicitly why there's like two edges coming out from these states is because the Alice's matrix contains only two non-zero elements in each column, and they're all very simple. They're just 1/2. So that's what those 1/2 correspond to. Okay. So this state can transition either to this or this, equally likely. Right. For Bob, it's a little bit more complicated because he's doing some non-trivial rotation, so his matrix is much more involved, but so that it has more edges. So basically, you get.
Is it always 3? I didn't look at that matrix.
You can see. I think it looks like there are 4 non-zero.
Oh, 4. Yeah.
Yeah. It is 4. Yeah.
It's always 4. So okay.
There should be 4 edges from outgoing from each vertex on this last layer. Yeah. So purely technically, it's like after you get this last joint distribution, you can recover. It's like you get, if you just run it, like I done it here, just run this circuit, you get some tensor 8 by 8, right? But the way you can encode it as a sign tensor, because I shaped it in such a way that you can just reshape it into this dimensionality, and this 2 basically would correspond to the sign.
Okay.
Or the color of the sectors. It's either going to be a positive or negative. So you can just recover from the indexing into this tensor, you can recover the sign of each of the outcome. And you can just, based on the sign, you can just count it and actually recover, introduce the actual sign, because if there is an odd number of negative outcomes, it's going to be a negative. If it's even, it's still going to be a positive. They are multiplicative. So it's like if you have a state with 2 blue outcomes like this is actually counts as a positive outcome, because those 2 negative ones multiply together to get positive one, right? And that's how you algebraically recover our original distribution from this combined negative one. You just introduce this sign, and you get the same kind of winning rate and all that, right? So this is like the technical details of what's happening. Then after this, it's only speculation, and you can think of actual physics and trying to interpret this result, just like with some fun interpretations. Because obviously this kind of separation into positive and negative outcomes, it's seems awkwardly similar to like particles and antiparticles. So you can imagine they like annihilate with each other, so that essentially we recover our positive outcomes because we somehow only post-select on the positive outcome. So we essentially, every observer invokes some kind of survivorship bias for selecting only positive outcomes.
Well,
but all the negatives.
Yeah, isn't it the action of us as observers doing that? Like us as the experimenters, like the person doing the experiment.
In a way, yeah, maybe it's like very implicit, because we're already starting our experiment from a positive sign of our universe. It's like we assign it some kind of sign to it, right? And then we perform an experiment. Sometimes our quantum experiments can flip the sign of the outcome, right? We don't observe this difference, but when we combine some of them together, like from two locally, like spatially separated measurements, right? We have to multiply those signs, but we post select for only positive ones, and effectively all the positive and negative annihilate with each other. It's a little bit weird how it happens. I don't know how to well explain this mechanism. I have some like weird pictures in my mind how you can maybe make it less contrived and all that.
Yeah,
And maybe we can add some more details.
yeah. The narrative element is the part where it gets like paradoxical. If you go back to our stream on quantum paradoxes, the way Mads was explaining it is that the maths is right here in front of us. Where it gets tricky is trying to explain the narrative in a physical sense of what's happening. Like, where's the cat? If you open that box and but sometimes the cat's there and sometimes the cat's not doing so well, and sometimes the cat's fine. It's like, if you try to explain it in terms of these anamorphized explanations, it gets tricky. Memes is asking, where do we place the burden of computation? The burden probably of computation, observers or universe. Where do we place the burden of computation?
Well, maybe the question is about why essentially quantum computation is supposedly more advantageous over classical one, right? That's why we're trying to build the classic quantum computers. But here I explained it as though you can do it, the simulation purely classically by just sampling over this multi-way graph, because you can sample. If you want to sample from this final distribution, all you should do is just start with some sample here, resample it every time you apply some stochastic matrix to get the final, the sample from this final distribution. Yes, that's easy, and you can perform it classically for arbitrary large quantum circuit. But the catch is that when you get the sample from this distribution, you still have to recover from it somehow the sample after annihilating all the positive and negative outcomes somehow, right? And that's computationally very hard to do. It's even numerically non-stable. It's if you like sample from this distribution if you sample a bunch of outcomes from this distribution, you won't recover with good approximation the difference between them. Like if you actually assign some sign to it and compute the difference.
Do we need that for each of the results? Don't we just need the end result? Like, what if we merge all of those final stages into 4 again, and then during that merger process we create all the annihilation we need?
Well, it's not all you need, because you compute the statistics. Like, imagine that you just sampled like 1,000 of those doubled outcomes, right? Now you have this distribution. It looks like this now, right? If you actually just show the underlying state vector, it's going to be very boring, uniform looking thing like this, right? So it's like mostly it's a distribution over these outcomes. Maybe I can show it like this amplitude plot. Yeah, so you see, when I rotate them, I think I can. Labels, angle, minus -2. Yeah, well, a bit better. Right? So this is like those all possible outcomes with their corresponding probabilities, right? So you can sample from this distribution even classically, but in order to recover the distribution like the one that we want, like this one, right? You need to essentially exactly cancel out all the positive and negative ones, right?
Why exactly? What if we just do randomly?
Well, randomly, it's just precision is going to be very horrible. It's like exponentially gonna it depends on how many samples you get. It's like very complicated. Even in usual physics, when people try to measure difference between energy levels, I think it also relates to that. That the measuring the energy is much simpler than measuring the difference between those, right? Because if you, this is kind of the same phenomena here. If you have only approximate distribution because you sampled from it, not because you don't have the actual numbers, right?
Mm-hmm.
The problem is the first kind you have the problem of vastness of the space, right? If you have 100 qubits, right, and you encode it like this, that each of them is 8-dimensional, right? So you get 8 to 100 number of possible outcomes. Okay. So you can't really store it as a probability vector on a classical computer, right? So that's why you can't directly compute using tensors and just like dot products of matrices, the actual distributions. That's why it's complicated. Though you can do is sample from this distribution, like maybe take a million, a billion of samples to approximate it. But in this case, if you have the exact sample, non-biased sample from this distribution, you still have to recover a good sample from the distribution that you get after annihilating positive and negative ones. And this one is like destroys all the precision basically, because you have to have like this approximate number of samples in order to get it right. Otherwise, your samples are not good.
Isn't it kind of like philosophically profound that computational boundedness has some kind of connection to quantum information?
Well, perhaps yes. Not just information, not the quantum information. Just information is very fundamental concepts for all the physics. Right? So here, trying to just get sense of it, because especially we want to make sense of the quantum information, and I'm claiming that the only conceptual difficult part is the sign and the possibility of probabilities to destructively interfere with each other. And we basically, instead of like using all the complex amplitudes and thinking of them waves interfering with each other, we reduce the problem to just the nature of signs and like positive and negative signs. So you basically have discrete states, they equivalent up to some sign, and if they're equivalent and have opposite signs, they essentially they preclude each other in a way so that they don't matter and they never happen at all. It's like they don't even exist in your multi-way system. It's like two different histories, two different possible histories with opposite signs, but leading to the same state.
Isn't it almost like an equivalence in where you take a certain path here based on an updating rule that's there's another option to apply the updating rule differently, but in the very next step you apply the opposite paths step first and then the opposite path step second. So they're equivalent in terms of like what happened with the updating rules, but the paths put you in the exact same spot anyway afterwards. So it's like a opposite updating rule application, like the order of application is separate, but it ends up in an equivalent state.
Well, you can certainly think of it some kind of process going backwards. So also, we can speculate and try to come up with a good narrative. What does it mean? It's like even all the Bayesian interpretations in a way hint on that Bayesian inference, the word inference already means that it's some kind of encode the backward process of your probability distribution manipulation that you're going to do. Right? As opposed to just going forward and applying the stochastic matrices like this to your underlying distribution, you have to also be able to go backwards.
There's like an external observer that's validating your Bayesian inference or something. There has to be some kind of validator, some kind of external objective observer. Is that accurate to say it that way?
validator. Well, there is like an interpretation of quantum theory called transactional interpretation. So in a way, you can also call it. This has to happen at what has to happen is a transaction between your initial and final states. Then there's no like only a forward process of your evolution. There's also some kind of reflection happening, right? So basically, a transaction happens.
Does it
not just
does the transactional interpretation is that opposite to
while this transaction happening, there's some interference going on.
Yeah. So is that transactional interpretation a different interpretation to the many worlds interpretation? Is that like do they diverge in terms of it's either transactional or many worlds?
I have some.
Oh yeah, I can see the connection is starting to stutter. There we go. You're back. Okay,
I heard you. Yes, it's just your video is froze.
Okay.
The many worlds. I'm back here, right?
Yeah, it's just a bit of delay at this point. Okay. Maybe if you want to stop sharing for a moment as well, we can discuss this and maybe bring up the whiteboard as well.
Let me do.
Just see if we can get the quality of the connection back. Is there an interesting way to partition data in an interesting way? Yeah, I mean, that's basically the whole idea of doing this probability way of figuring out the CHSH game. Okay, how's the connection now?
I don't know. You tell me.
Okay, seems a lot better. Back? Yes.
All right.
Okay.
I just disconnected my VPN. Right. Let's go back to sharing this. All right.
So yeah.
Your question was about how the many worlds and interpretation and transactional interpretations are similar, right? Well, in a way, what I'm trying to kind of make it more explicitly here, it's because many worlds for me was kind of always confusing, and I think not just for me, because there's like multiple versions of it going around without clear picture what actually is branching, when the branches is happening, how they merge or what shouldn't they merge or not. So it's very confusing.
So what you're saying is that there's many worlds of the many worlds theory.
Yes, yeah.
Okay.
So
makes sense.
So here is just like I reproduced it like explicitly. It worked. I can potentially do it for any for any quantum experiment you can imagine, right? This is the most interesting because it involves all the problems of locality and reality and all that. So that's why we're investigating it. But you explicitly show what the branches are, by just probability branching, because we reduced everything to probabilities. But now you just have all of those paths to your final states, right? So all those possible histories producing some special states. And we just have a problem now how to interpret how those histories essentially can preclude each other and interfere. It's like, for example, in quantum logic, there's some language that can help here. Even in classical probability theory, there's like a language of talking about events, not like space-time events, but events as, in this case, just subsets of histories. It's probabilistic event, a thing that can happen, right? So it's like, but because it's like instead of your elementary outcome, which is your single history, right? Single history produces an elementary outcome. Each subset of histories is your event, and you basically form some kind of logic around those events.
Almost like the causal chains. The causal chains are the events, something like that.
This is, I think there's like confusion between what events are, right? There's a space-time event, which like in our picture, at least it's clear, it's a space-time event corresponds to an edge of your system of actual thing, like rewriting of this state to this state, right? So each edge is our space-time event. In the logic case, probability theory case, the event would be like a subset of histories, right? So it's a little different thing, and it's like because you usually axiomatically introduce your probability theory by introducing a sample space. In this case, it would be a set of all the histories, and then your event space would be like your power set of that set, right? So basically, all the subsets, all these sets of histories like that, and then you combine them together, introducing a bunch of axioms out. You can take union of that, intersection, or an AND, basically do the logic with those histories. It's just quantum logic is going to be different because how you can how you can explain this preclusion of, because that's I think the word they use also, of that you actually can have a measure of zero because your two events can together don't happen, right? Even though one individually can. So this is like classically is a contradiction, but quantumly it happens. So that's why you need like an additional logic essentially if you want to express these ideas.
So is it a different type of axiomatic? Is it like a different type of gate that only exists in quantum logic, or are you just using standard logical operators to create that quantum logic?
But you still use the same kind of operation. It's just the kind of axioms should be different, because under classical probability theory, this kind of case cannot happen when you have a plus b equals to 0, but a and b are not 0, right? Something like that. But this is obviously not the case for this case when you deal with these quantum events as histories of your.
Can that sort of interaction happen in complex numbers? Is it possible?
Yeah. Complex numbers is just like a tool that makes mathematics easier to deal with, even though conceptually that is not required. Right. So, because we can like, if we wanted to, we just can traverse. We could have invented quantum theory by just like postulating this kind of possible histories with positive and negative outcomes, and then discover or invent a way to make it into a nice Hilbert space, and then reinvent all the quantum theory as we know it right now, with all the brackets and Hermitian and unitary operators. And now it's just going to be computationally more attractive.
Okay. I would like to explore some ideas on like a very simple version of what seems to be a quantum effect, which was it's kind of like a simple version of the double slit experiment where you evaluate when negative probabilities can exist and the link to that and the link of that to ambiguity of which way path information. So yeah, I was thinking that there might be a way to create negative probabilities where they don't exist, and maybe you can help explain the thinking behind that. And there's also some probability ideas in there. And we can come back to this one. Is there anything else on this notebook that we haven't covered, or is this basically the full notebook?
I think that's it in this notebook.
Okay.
The rest is just talking, or maybe it depends on the questions.
Okay, cool. Let me bring up the whiteboard here quickly, and then let's draw some pictures.
Yeah, let's do that.
Okay, new whiteboard. There you go. All right, so let's think about double slit experiment. So let's say you have do like a gun. Yeah.
And think about the free slit experiment. I've shared a paper recently in our channel.
Oh yeah.
By Sorkin. It's essentially about, it contains this breakdown of free slit paradox. Let me just copy the image here. Oops. Can I paste the image?
Yeah, you should be able to. Just make sure you copy it.
About the screenshot. Okay.
Oh, that's interesting. I saw this in the paper. Yeah. Do you want to explain this this image a little bit? Why is there 3 slits?
Well, that's just the setup, because with 2 slits, if you just want to reduce the problem, you get only 2 paths. If you just reduce again to the single detector and the single source, then like some simple probabilities as signs, you can't really recover this nice destructive interference, right? Because with 3 signs, you can do +1, +1, -1 gets you 1. So it's essentially a valid quasi-distribution. So that's why this 3-slit experiment paradox is a better representation of the problem with negative signs. Okay.
For the double slits, yes, you're right. That actually makes more sense. I guess what I was trying to do is not a double slit experiment, so that's probably why it was confusing when I mentioned it. So let's try this version, which you're right is not actually double slit. And now I have to think carefully about my colors to make this be obvious. Okay, so now from this original split here, you now go into 3 potential outcomes. So the one outcome, the one split is this way, but on this side, let me do these colors kind of like the same. Those merge and this one diverges. All right. So what you have here is probability distribution between A and B. And then at the end, you have a probability distribution between, let's just write these as 1, 2, 3. So 1, 2, 3. Okay. So there, this is combined and this is combined. Now, what's interesting with this type of experiment, so it's not working, is that if you were to cut off this side, this B over here, so let's say you just stop the photons or whatever these, yeah, let's just call them photons coming through here. Then what you have is a probability distribution of 1 here and 0 here. Let's do probabilities as a different color. Let's say yellow. Okay, so you have 1 here and 0 here. And then let's say you split this into 0.5, 0.5. So 0.5, 0.5. All right. Okay, happy. So sometimes they end up here, sometimes they end up here. Then what's interesting is if you were to remove this block on this side, and then say you, so let's do another version of this. So that's version 1 where it's blocked, and then version 2, it's now unblocked. Okay, so let's put that back for this demonstration. And now you change these probabilities a little bit at the top, obviously because there's no block anymore. And then let's say this becomes like 25, so 0.25, and this is 0.75. Okay, and then up here, what's interesting is that for this to be a valid probability distribution, the end result has to be positive. That's important. And these have to sum up to 1 at the end here, because there's a P of 1, right? That it will end up in one of these places. So that's like unavoidable. You have to get to 1. That's a 1. Okay. Now, what happens here is that you end up having 75 divided by 2 here. So what does that become? That becomes like 0.35, I guess. And I might be wrong with my maths, so just help me if I'm doing this wrong. But that becomes like 0.35, 0.35. No, okay, there I'm already wrong. 0.7.
Well, you want to multiply it, right? So you should have or divide it by 2. Technically, it's like 375.
Okay. Now on this side, we need to get back here, but this distribution doesn't have to be it doesn't have to be 50-50. So let's say it's a little bit different. Let's say this is 90-10. Okay, so then let's say that was just the distribution at this point. So the end result is going to be
Hold on, are you now labeling the probability of what, branching, or the last probability distribution?
Yes, that's a good point. That's a good point. Yeah, because it was 0.5 here and it was 0.5 here. So this is the end result. That's important to explain. And the reason it's important to explain is because what you're looking for here is the change that this new path information has brought about. So let's, for simplicity, make this 0.5 and 0.5 and 0.5 again. I should have prepared my my presentation a bit better, so I didn't have to figure it out as I'm going here. But let's just say this is 0.5 and 0.5 as well. So what you've ended up doing here is you've taken some probability from this path and you've shifted it into this path, which means this previously was a 0.5 probability of going this way. But in order to get from 0.5 to 0.375, you have to have introduced a negative somewhere here to reduce this probability. So going down a different path means that the combination of this blue and purple has resulted in some kind of negative probability being introduced along this path. So this is where negatives start coming into the picture. So what is that? -1. Okay, I'm gonna use my calculator. Yeah. So figure this out. So once all the numbers are on the screen, then then the narrative becomes easier.
Yeah. Well, for me, the motivation wasn't clear because you still have no like unity on the last distribution. Like it's not. What is the probability at 0.3? It's 0.25, right? If you want to sum up to 1.
This one over here, yeah. So this will be 0.25 multiplied by, yeah, so this is exactly 0.3. What do you say? Oh, 0.3. Which means that this has to be greater than 1 because it's just 0.5. Yeah.
I'm too confused now already.
Hold on. I'll get to now. So what you're saying is this is 0.25 multiplied by 0.5 is 1.25. So to get it to 3, 0.3 divided by 25. It has to be something like 1.125. Yeah. So this combination over here gives you a probability of 1 again. And then this probability here also gives you 1 again. So the interesting part here is that how the change from having just a single path on this side, okay, the change of now opening up the possibility of a photon traveling down a different path and then ending up in the same position allows for one of those paths to contain negative probabilities.
Yeah. Should you also like subtract here something like 0.25 or something like that?
Yeah, on this side. Yeah. Well, that's
no, because in order for all of this to equal to 1.
Because this is 0.75. Sorry, this is 0.75, and this needs to be 0.25.
Or so maybe, yeah, yes.
It's so funny. The source of where I got this was from a YouTube video, and similar to what we're doing now. And there was a lot of small algebraic corrections that you had to do afterwards just to make everything work out. The moral of the story, though, is that this purple path over here ends up being a negative probability. And the point is that this becomes a negative probability because there's a path that exists on this side once you've opened it up, which takes probability away from here. All right, so let me draw a different picture now using the idea of what's happening here.
I don't know. Numbers are still very confusing. So it's like
picture. I'm good with pictures. I'm not that good with numbers. So you can figure out the algebra. The concept makes sense though, right?
Oh, even the concepts is kind of also shaky.
Think of it this way.
The path.
Yeah.
I understand it's like you technically can shift. You can introduce negative probabilities without destroying this nice property of your final and intermediate distributions being positive and sum up to 1. Right? The intuition about diverting this flow of probability by abstracting some paths, maybe, yeah, it's kind of, it's neat. It's just physically not clear how it happens.
Yeah, so it happens like this. In the first example here, this was closed, and this was your window through which particles could flow. So what you're doing here is, as you're making this window a little bit narrower, you're opening up another window on this side. And by opening up...
yeah, like it's kind of clear. It's just, are you drawing the probabilities of like aggregated across the path, like the final, including like 0.25 and 0.75, like after you multiply them, or you those are aggregated, or not the, because if you just fix your experiment setup, whether you abstract your path from S to B or not, shouldn't change the probabilities of B to 2 or from B to 3, right? So those probabilities should be fixed. It's just like the aggregated probability may be changed when you open up some additional path.
Yeah, it's the aggregated possibility, because what happens is some of the particles that would have ended up at 2, because this is open, end up at 3. So there's a total reduction on the, let's call it the left-hand side of either 1 or 2. There's a total reduction happening here.
Because when it just multiply it, then it's like you have a 0.25 to go from S to B, right? And the original was 0.5 to B to 2. Why it's not just multiplied? Why do you have to change it to negative?
Because somehow you have to reduce the probability of
maybe it's like you
implicitly.
Maybe you're already implicitly doing this backward inference because you're trying to fix your final distribution and then what would be the probabilities.
That's true. So actually, the narrative here is that it's not exactly 0.125. The point is that there is a set of probabilities you can apply to the paths that allows you to have up to negative 1.25. That's so you could randomize the probabilities like however you want. It's just that it's interesting to note that there can now exist valid negative and positive probabilities. That's the interesting thing about this which way path information, is that this becomes a valid probability. Previously, if this wasn't rejoining here, this negative probability wouldn't be allowed. So there's something about the fact that this path information is recombining here that allows for there to be valid negative probabilities.
Yeah, I think there's some actual mechanism is missing from this description, because even quantum theory tells you there's a the actual constraint, which are the actual constraints of those probabilities should be in order to be valid, right? Because if like I showed, when you convert your quantum state with complex amplitudes into phase space with quasi probabilities, even this transition you can do for every quantum state. You can do it in reverse for every quasi-probability distribution. It's like if you give me an arbitrary distribution that sums up to 1,
Mhm.
it doesn't mean that it's going to correspond to a quantum state. So it's not like 1-to-1. There is like basically some invalid distributions in this sense. So conditional or just overall for states are not every distributions are allowed. So there's like a constraint embedded in the formalism of quantum theory.
Mhm.
Here it's not visible. We just say this somehow it is done.
Yeah,
Right?
I think the interesting thing was that there's some kind of interesting sort of space over here which one could think of in terms of like a double slit experiment, saying when you don't know which path a particle traveled through, you kind of like where you erase which way path information, quantum states emerge. And just with this simple setup, you could say that when it's ambiguous which way a particular probability distribution traveled through, there is negative probabilities become a valid potential probability. So that was the analogy used there. We're not saying that that is exactly how it works. It's just it's interesting to think of it in terms of this situation where there's ambiguity of possibilities that are sort of forced to emerge to be recombined at a later stage. It seems like that's where negative probabilities emerge or quasi probabilities. So we're not saying all quasi probabilities are quantum. It's interesting that this which way path information produces these quasi probabilities.
Right.
Okay, so all of that was just to say that there's this idea I had in the Wolfram Physics project where, let's say you have a and you can help me with maybe the wording of this, but let's say you have these updating steps where we think how can I draw this? So there's some kind of state that gets updated into let's just redo this experiment. So there's 2 possible states here and then 3 possible states again at the end here. And if we think of the probabilities simply as what I was going to say, like as degrees of freedom, or just number of potential applications of a rule, something that leads to a second stage. And then okay, so what does this add up? That adds up to 6. So let's just make it 10 is going to be a weird number for 2, but 4 and okay, whatever. The more interesting part here is on this side. So let's say we have, okay, so now I need 15 altogether. 1, 2, 3. Let's make this 2. Let's do 4. Now we have 6. I'm going to go 2 here. So 2, 4, 6, 8, 10. Okay. No, we need more. Sorry. So this is 1, 2, 3, 4. Let's do 1, 2, 3, 4, 5. 6. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, whatever. We'll change it. The point is that there's 15 states here. Okay, so now just based on the degrees of
why state?
Sorry, updating potential. Potential.
Updating what?
Let's say degrees of freedom. Now, what happens here is that the right way to say it?
Well, the degrees of freedom. Wait a minute. Just say like rewriting rule, updating length. I think that's what you mean, right?
Yes, I mean the analogy to probability would be to say that there is a rule that exists that could be applied down one of these routes. So let's say if this route is taken, this is now your current state. So you can't take this route as well because you're already at this state. Now, if you're just let's say an observer traveling down one of these routes. So just the fact that the rules that could apply when you're at this state to get to this state are 1, 2, 3, 4, 5, 6. So there's 6 potential places that your updating rule could bring you to this state, and there's only 1, 2, 3, 4 on this side. So it's sort of like degrees of freedom that allow you to move here. There's 6 degrees of freedom to get to state 2, and only 4 that gets you to state 3. That's why I was trying to like make this probability assessment. Now, I believe some of the difficulty with thinking about this in terms of quasi-probabilities is how do you assign negatives here? And how do you actually get quasi-probabilities? Like how does this arbitrary become like -1 and like +2, 5? And like how do you actually get numbers?
And effectively, at least.
Yeah.
Right? Because you know how to count. Like you know how to count paths. You don't know how to assign signs and
yes. So this was my thinking. So my thinking is that there exists an observer. Let's treat the observer here. It's blue. Okay. So there exists an observer that's witnessing these updating events, but the observer is computationally bounded to only be able to see 10 paths at a time. Okay, so it's a 10 path computationally bounded observer. Okay, 10x paths. Okay, so now what happens is at this stage you can kind of see everything, maybe in more detail than is necessary, but at this following stage there's only 10 paths you can see. So there's some kind of equivalency that takes place. Now we have to say there's only 10 paths. So from this computationally bounded observer's perspective, there's some kind of equivalency that takes place that says, okay, maybe here's the lowest one. So maybe there's 1 path here. Maybe this has got like 2 paths or 3 paths. This is maybe 2. So now it's 1, 2, 3, 4, 5, 6, 7. Maybe this has got an extra one. 8, 9, 10. Okay. So now what you've done is this is kind of in a more fuzzy way, a more coarse-grained observation, what this third-party observer is experiencing. Okay, now here's where the mathematics comes in, and again, I'm going to try to think in terms of numbers, so this might be tricky. But if there are 15 paths here, and the observer only sees 10, then if you do the maths and you say 15 over 10, you're getting a 1.5 kind of value on each of these paths. So let's say it's 1.5 here, 1.5 there, yeah, 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 yeah. Yeah. Is that right? Okay. Now, my argument is that some of these are going to, because they're equivalent, let's say, let's take red. Let's say, and we make this a pen. So let's say back to red, quick scattered draw. Okay, so let's say this one and this one have to annihilate. So there's some kind of negative interaction. This one and this one have to annihilate because this path, at least 2 of these paths are now equivalent in terms of which way they went. And what you're left with is 1, 2, 3, 4, 5, 6, 7. Now, does my maths work out? Wait. 1, 2, 3, 4, 5, 6, 7. Yeah, there's definitely negatives I've added up here. In other words, when you coarse grain, you end up with 1 probability, because over these 10 coarse grain paths, your p equals 1 again. But in reality, the numbers are greater than 1, which means some of this annihilation introduces negative interactions. That's the thinking. The numbers don't work out, but that's visually how I'm interpreting it.
Well, let's just straighten this observer thing. So you imagine it like some kind of external observer, right? But it's like each path here is actually corresponds a global space-time change, right? In a way. So we kind of should imagine, I guess maybe it's helpful, that an observer lives along those paths, right? So he only exists on some of them, on those that you highlighted.
Right? One observer, not
one observer. Yeah, it's a single observer, but because of the branching and possible different ways you can update your space-time, it essentially can exist on multiple alternative space-times, but only on a finite amount of them for some reason.
So that's observer A, and then blue would be observer B.
Right, so we want this kind of to build some kind of internal picture of an observer and to make it bounded. That's what we're trying to do here. Right? So if our black edges are the actual all possible alternatives that can happen independently of an observer, right? The boundedness of an observer limits our access to all of the branches. So that's essentially, we want this be interpreted as this occlusion of some of the paths and the emergence of negative probabilities. So that's the idea, right? We just need to make this a little bit more quantitative, numbers to make sense of numbers. How we can do it.
Yes.
Yeah. So okay, let's do it.
Let me use my calculator.
But just label some sensible things. For example, like if you have 2 edges here and 6 in total on the first layer, then it should be 1/3 probability of going left, right? 2/3 going right. Okay, let's just do the same kind of thing here. This going left. If 5 edges you have here, this would be 3. This, right? This would be, how many in total you in this example have? 6.
1, 2,
10,
3,
right?
4, 5, 6. Yeah.
So it's 4, 10 for 2/5. This means this one is 3. It's kind of the same probability as on the right, just with different counts.
Yeah.
Right. So if we constrain our observer to only have 10 possible histories at once, he only lives in the. So in the first layer, he's contained, or observer contained in every path.
Yeah.
Right.
Yeah. You can see everything.
Here it contains only in those ones. Essentially, like the left one, he observes completely. This one, only half of it is observed.
Potentially. So like how you would actually apply those thicker, coarse-grained paths. I was just using for illustrative purposes here. I think you can apply. You should be using mathematics to determine what the actual probabilities were that were coarse-grained. So that's why I did this 15 divided by 10 here. In other words, saying there's 15 actual paths, but only 10 were merged. So on each one, Wait, is my maths wrong? 15 divided by 10. Yeah, it's 1.5. So
Yeah.
yeah, so the on each black path there's a 1.5 value. And then
But
what's
just I'm not clear what this value is supposed to be.
I
It's like your
guess
total value. If you want each black is now 1.5, then you need the total value is weird, right?
okay, let's see, this is 3, 6.
Maybe
So this total value is here is 6. This total value here is
if it was instead like 2/3 or something, so that 10 over, if you divide it that way around, 10 by 15 and assigned this value to each of the black edges so that they all sum up to 1. That would make sense to me. But the other way around.
yeah, the reason why I do it this way around is because this is what gives you the negative probabilities or the negative interactions where the paths recombine. That was the whole idea here. So this is 3, 6, 9, 12. No, it is 12. 1.5. Wait, 1.5. That's 2, 3, 2, 3, 4, 5, 6. So let's just go 6 times 1.5. That's 9 plus 3. It's 12. Wait, is that right? Did I mess up something?
Oh, I've lost track completely.
I'm just trying to work out the
What you're trying to do.
The values here. So 4.5 plus 12 plus 6. Yeah, so in other words, you need to go from 22.5 back to 15. And this is where this annihilation happens here. And you minus in 6. No, yeah, 6.5. Okay. I guess I'm also confused. The narrative makes sense in my head, the math doesn't. Okay. Check this out here. I think what I'm trying to say is that you need to get more than you need to get like somehow above 1 so that this recombining gives you negative probabilities. And in that way, you're not applying, it's not like you're applying some negative numbers to the paths arbitrarily. It just ends up being negative because the paths are equivalent. That's how I was trying to get the negativity, like these negative effects going in. Like the annihilation happens because on recombining the paths, there's sort of equivalent ways in which the observer could have gotten there, and then that reduces the amount of potential paths that were happening. I was just adding this outside observer to somehow get you back to 1, because otherwise you could have as many paths as you want here, and you're not going to have this constraining of possibilities. It's somehow like going from 15 to back to 10. There has to be a reduction. That's what I'm trying to get to. So there has to be some kind of reductive force getting you back to a total probability at the end of 10. Because all of this here, from the perspective of this observer, in total is 10 paths. So they must end up being like, yeah, they must end up being 10 potential paths of information. So how do you get from 15 to 10? That was my question. Some kind of reduction has to take place to get you from 15 actual paths of the observer that traveled through this multi-way system to 10. So I was just trying to go 15 divided by 10 to give you some kind of way of reducing the possibilities.
Yeah, just this factor seems other way around. Like if we would just watch like on this different paths that observer can take, like this. Oh, wait, so pick here. This one. This would be 1/5, right? Versus 4/5. Like the black probabilities are without an actual probabilities, but an observer, due to his boundedness, observes this one, and there's like an effective reduction because you get basically twice as less probability over here, right? That's what you're getting at, and also here. Another way around. So what would happen if you actually compute the paths here? Now, in this branch, you have 1/3 times 3/5, right?
Mm-hmm.
This, you have two paths over here. You can take the left first, go this, or you can do this times this. And here you can do thirds times thirds, like this. This should sum up to 1, right? Hopefully.
Five. So that's 0.2 on the left. Maybe we should do this on notebook.
Plus. Oh, this is weird.
5 times
3/5.
Does anyone in the chat who can do the maths quicker? It's 0.08. It's 2 divided by 25. Is that right? That's right. 1/3 times 2/5. Oh, plus. I missed the addition. Over 5. So that's 11/15. Yeah, just like that.
Oh. Increase.
So 2 divided by 3 times 5. 8/15. Yeah, okay. I think we're going to be. And then the last one was 2 divided by 3 times 2 divided by 5. It's 4/15. Yeah.
Observer.
This is saying, so very simplified, you could end up with a sort of anchor shape with the convergence at the top of the anchor. I think I just accidentally stumbled onto way more understanding than I expected. I went from what grew with banana pigtails to peel soda and C. The peel soda and C is not a wrong way to describe what you're doing with the black points. I could be totally wrong, but I think it's basically on like 5L level. Okay.
Why?
What it is 8 over 15, right? Oh, do we have to change it?
For the black branches, it's 8 over 15, right? But for the blue ones, it's 9. So it's like an increased. But it doesn't change the probabilities on other branches. So it's like stop summing up to 1. It's kind of a bit confusing. So it's like renormalizes it by some intuition here.
Yeah, so I mean the thinking here is that actually this is the part that I didn't explain clearly, is that it's not just that these two branches over here become 1. Let's say like it's not just that these two become 1. What you have is, because it's equivalent across the branch, there's an equivalency all the way up here. So in other words, somehow we need to make this bigger and say that one of these equivalence branches is like this. How do I make it bigger? I have to think about how to visually do this, but it's kind of like this branch connects to that branch there, right? And it's now seen as just this one. And then there's another equivalency maybe here that's taking this branch and adding it there. So there's kind of like this mixed state that happens because of the coarse graining that mixes some of the branches here across which way path information. So in other words, if you squint your eyes enough, which is what it's a type of coarse graining, right? When you really close your eyes.
Squint your eyes, yes.
If you squint your eyes enough, some of these paths end up being 1. So instead of, so let's draw this like this. So now those black paths, some of them end up doing this. It's like 1. You don't really know which way it went. All you know is that there's certain paths that went from A to 2. But you don't know if it went this way or that way. So you effectively create a kind of like a reduction going in here. However, you cannot deny that some of the results did end up here. Okay, because at the end you have the total results here of like 3 potential states. So you're always going to end up here. It's just because of this coarse graining, there's like this merged state over here, which is where the negative, the reduction or the, some kind of like negative effect has to happen with these pathways, with the black pathways. Because it's not 1, 2, 3, 4, 5, 6, 7, 8. It's not 8 pathways anymore. To get the equivalent total pathway, you've reduced it to maybe 1, 2, 3, 4, 5, 6, 7, 8. So you've gone from 10 to 4 here. So you have to go 10 minus 6 to get to 4?
I'm lost.
Okay,
nothing makes sense anymore.
Okay, so think at the top here. So you had how many black pathways? 1, 2, 3, 4, 5, 6. So you can still say that there's 1, 2, 3, 4, 5. Yeah, so you have to. Okay. Let's draw another picture. It looks like a dancing trefoil knot. Okay, let's try another. Let's try another intuitive.
It's like from this little computations we did it's like at the bottom. It's like the only effect I see clearly is this: if you constrain your observer, his probability essentially increases in some branch relative to the actual probability ending up in this branch. I just don't know how to interpret the physics a bit. It's like, what does it even mean to be constrained?
Okay, so I thought about that as well. Here's my idea. I'll put it to the left here, since we're talking about this observer. Right, so what it means to be constrained is kind of like maybe the radar analogy. So I'm going to use black and blue here. So let's say you have a state here, and there's an updating rule that lets that can be applied going into this split here. But there is also an updating rule that somehow takes you to this external observer here. Zoom whiteboard. Yeah, so that's it, is this observer here. And then what happens is there's other rules that go here, like we showed with this updating step. Let's just do like a simplified version. Okay, but now whatever rule took you to this blue observer here on the side, this external observer, at these two in-between states, there's no rule that can be applied that has any kind of relationship yet to this blue observer. The only next states of the hypergraph where this blue observer can interact with the state of the universe again is at this step. So there's this kind of like there's this unknown state here. There's this unknown.
Is it supposed to be a multi-way system or what?
Yes, it is a multi-way system.
This is just something like interaction. It means just they produce the same state somehow. So if you describe your blue state as some state with your what you call an external observer, you basically disappeared in the black state.
Yes.
So those. So just like a temporary.
There's no interaction.
A virtual particle there.
Well, there's no causal connection. There's no causal connection is what I'm trying to say. So
between what? Between edges, blue and black edges. There's no causal connection.
In this state. So in other words, to get to this, okay, let's say this is state 1, this is state 2, sure. This is state 3. So to get to state 3, the blue observer can only get to
a single state. There are 3 states in your third layer, whatever.
Yeah, there's 3 states. Okay, so let's say there's step 1, step 2, step 3. So there's 3 potential states at step 3. Okay. Now, to get to one of these 3 end states, you can either take causal steps here, which ends up in this final state that has a causal connection to 3, but if you apply the rules that take you to these black states over here, there's no rule that can take you from these states. There's no rule you can apply as a third step that has a causal connection to this third observer. So that's where the kind of the which way information becomes that's where ambiguity takes place, basically. That's where ambiguity, that's where this ambiguous information happens. You could even say, so maybe another way to say it is that the rules that take you to, let's create some actual names here to make it specific. So this is A, B, C, D, E, A. So the rules that take you from A to A or to B, okay, there's multiple degrees of freedom that whatever rule you apply to get you from A to B can be applied. So there's multiple degrees of freedom. But the same state in C, there's maybe a coarse-grained limited set of degrees of freedom that can be applied. So if you apply the rules that take you down one of the black paths, you have like a lot more degrees of freedom. But from the perspective of C, if you're this observer here, there was a limited set, there's less rules that could get you to these final states. However, from the perspective of the person doing the experiment, so us over here, if we say we're putting ourselves in the shoes of C, okay, this person could only coarse grain what was happening. And if the actual result was one of these paths here in A or B, from the perspective of C, there was a coarse graining that took place. So it only makes sense to talk about a coarse graining from an outside observer because we know coarse graining took place. If you were sitting in C's shoes, no coarse graining took place because it only saw the pathways and the rules that could be applied to C. Us as the observer says actually what was happening, if any of these routes here through A or B was the official route that actually took place, C wouldn't be able to tell it went through A or through B. It could only coarse grain one of the rules in its mind as being ambiguous.
Sounds confusing. Do you have like observers sitting on every state, like different observers, A, B, and C? How is it like C?
This is kind of
you're associating them to states essentially,
or rules, more like rules. Like this is a set of
the blue rules.
Yeah.
So the blue color is you're basically describing rules covered in blue as an observer.
Yeah. Exactly. So there's a set of rules that we could define as the blue observer's rules. It could be a single rule. It could be applied in different places in the hypergraph, but there's one rule that takes you. So again, I mean, this is where you can go back to the narratives and you can say, what narrative makes sense given some kind of objective mathematical reality? One narrative is that the observer are the rules or set of rules, and that they're experiencing a traversal of paths, and you just need to put yourself in the shoes of one of those observers.
So prescribing rules to an observer is a little bit. I don't know. It's like effective rules maybe, because we want to prescribe a rule to an actual laws of physics, and then observer just behave according to those laws. Maybe based on their structure and how laws acting on them specifically, the effective rules may change because of their constitution of how many, what kind of hyperedges the observer consists of, something like that. The effective rules are changing.
So here's my philosophical take on that, saying that if there's a hypergraph that represents the state, Okay, there are certain rules that you could apply to that state which could completely destroy the state to the degree that there is no state that exists anymore. And because a rule could be any rule, there's certain rules that completely swap every single current vertex and edge for a completed new vertex and edge. And the consistency of states is not guaranteed. But in applying rules, the consistency or the ability to apply a specific rule can be consistent, just in the definition of a rule being a consistent thing. So if an observer is that which makes multiple observations, then it would have to be something that could exist through multiple steps of computation. And the only thing that's guaranteed to exist through multiple steps of computation is the rule itself. That's why it makes sense that an observer performing more than one observation or existing at more than one time step to make an observation is something like a rule or combination of rules.
Well, where this rule is coming from is like, it's not, it doesn't sound very constructive. It's like if you have multiple observers, what, you have multiple rules prescribed to all of them?
Not necessarily. Not necessarily. It could be a single rule. I mean, depends how you want to, how collective you want to make the observer. I guess if you take the Reuliad as this space of the existence of all possible rules, then you could say...
Yeah, but you can think like of this argument that there are some rules that can destroy the whole hypergraph. If you want some description taking into account all the rules, right? You can make some argument about like this purely statistical survivorship of your hypergraph, because maybe if you even take all the rules possible within some computational model, maybe there's still some hypergraph that's going to survive it under just purely probabilistically. When you just apply all the rules to some particular initial hypergraph, there's just majority always going to survive, even though it's like at every step it can just be destroyed. But there's going to be more than survive, and if you focus on that and apply this like survivorship anthropic principle that, okay, we survived it at this current moment of evolution of this hypergraph, therefore it is.
That same potential exists for the rules, because one way you can think of, has the rule survived, is there a state where the rule can be applied to the hypergraph? So the rule exists just by definition through multiple time steps. It's just where the rule appears.
No, yeah, I'm just I think it's like not necessary construct. It's like you can basically effectively assign a rule to an observer if you again make it effective by the structure of the hypergraph itself. Okay, you assign an observer to this particular structure in the hypergraph, but if you are given an universal set of rules already, right, that you stick to, you can those act on this structure as some specific rule anyway. And right, so you don't have to assign like an actual rule to an observer.
You don't need to. You can make you can have the rule show up as a state in the hypergraph, or as a combination of, as a piece of information in the state of the hypergraph. The benefit of having the rule as the observer here is that you can kind of track almost like a specific causal pathway that ends up being one path as opposed to a different path. There's a thought experiment, a live thought experiment. Let's see what the comments are here. There's some comments about music, dancing, and the Velvet Underground. Perfect symmetry annihilates, asymmetry complexifies. Kind of. I mean, if there's a symmetric path that is equivalent and can be coarse-grained, then it will be coarse-grained. There's some kind of statement like that to say some of the which-way path information will be annihilated if there's a limit in how many ultimate routes
You
blue
like to use
observer could
this
see.
which way path.
Hmm?
Term, which way path term. You like to use it. I don't think it's used appropriately here.
Because which way was like it either took A route or the B route. So which way did it end up at E? It either went route A or route B, right? That's where I'm trying to think of like which way did it go? Did it take route A or did it take route B? The end result is that it ended up at E.
Yeah, you just a history. You can say it was like just a single path corresponding to one history of being an observer.
Mm-hmm.
Trying to describe, yeah,
and like there's some kind of blurry correlate like connection between the double slit experiment, because if there was some kind of causal observation here, then you annihilate kind of the possibility of there being ambiguous results. Yeah, that might require a bit more explanation for further stream once I've got some maths to prove my intuition. But there's something about the fact that you don't know. There's something about the fact that there's no information from the perspective of C that C can gather from either this A or B route that creates like a quasi-probability result here. That's the intuitional language that seems to fit in with this thinking.
Well, if we can bring it beyond intuition, would be great.
If I could do what? Beyond intuition, yeah.
Yeah.
I need to throw some numbers down here and get my calculator working. Probably a notebook is the way to do it.
This like global perspective of just trying to derive interference effects purely by boundedness of or constraining your paths or whatever. That sounds very appealing. I just can't understand how it can work yet. Right? But yeah, it's like I know Steven also has some kind of similar intuition, but I don't know how to make it show like an exact example that makes sense. I have like my example of reducing to these negative outcomes, and just beyond there you're kind of stuck unless you're trying to invent some branching, jumping between many worlds as an observer. Actually, there's like a good intuition I had today. So how we can explain this annihilation effects and destructive interference between branches that have opposite signs, right? So because as soon as you have this multiway system, normal multiway, probabilistic multiway system that has states of opposite signs, how do you imagine that you equivalence those states that are actually the same just up to some sign, right? Those are the potential states that the observer can travel between somehow, right? So you can imagine there's actual many worlds, but they in a way not too far away, but you can effectively jump between them. But because you're trying to preserve your initial sign being positive, you're only allowed to do this double jump, essentially, because it is you from the negative sign, in order to go to the positive sign additively, you need to go through two positive signs, effectively annihilating the intermediate one. So it's kind of it never present, because you had, in order to go from negative to positive, you have to go through it. That makes negative together with the positive you went through absent from the picture of observer that tries only be in the end up in the positive universe in a way.
Yeah. Right? So
this kind of
that makes sense here, where you could say the blue observer here can only traverse positive paths or something like that. So that is your coarse graining. Your coarse graining is saying I can only exist in positivity. You know, it's like an optimist. Like it just avoids all negativity and just.
It's just living. This intuition doesn't work. It's if you just restrict to the positivity, you not recover the whole interference, because how do you explain that there is some positive states are not allowed, based there's some negative, because there are negative paths existing somewhere else.
Yeah, there must be some cost of transversing the states. There has to be some kind of accounting that takes place. So you need to end up positive, but every time you jump into a negative path, there's a cost to moving onwards.
Yeah,
Something like that.
This like mathematically works out. It's like if you travel along time direction in your path of your multiway system, your signs are multiplicative. But when you travel in between those many words across equivalent states, those are additive.
Additive, yeah.
in a way,
yeah.
right?
Yeah.
So you have to go through multiple of them. Maybe you can even imagine doing some random walk around those equivalent states. But because you have to end up in the plus one sign at the end, you always have to travel.
Yes, you have to, because that's
even. Yeah, you have to travel through even amount of states, effectively like annihilating them, because they're never absent. You can't end up in one, and statistically that would lead up to this effective interference.
Yeah, that makes a lot of sense. And what was the thing you explained last time, that like what is locality? It's when you can create, it's when you have a tensor product.
Right? Yeah, it's like in this diagram when I showed A and B, Alice and Bob for tensor product together, we just have two qubits, they forming two systems, two qubits, I guess, in the end. Right? That's how you represent naturally different locations in space just as different quantum systems, because they form a tensor product.
So how would a tensor product form in this analogy here?
So here we if this represents states in the multiway system which are global, each point here, each vertex actually already is a tensor product, because it contains both Alice and Bob. That's what I've been telling you about, that the observer lives in all of those states. Any embedded observer. But if you just choose arbitrary history in this graph, in the multiway system, the edges doesn't necessarily have to be time-like separated. They may be separated in time. So this like red curve that you drew, right, containing two edges, those can be two events that are locally separated, space-like separated. Those may correspond to Alice and Bob doing their experiments in different locations of the universe, right? But you consider in terms of like a single history, you can flip them around, maybe under different reference frame. Because in a way,
so an alternate reference frame would be like, maybe this is,
well, you have to draw, you have to like first compile this multiway system into an actual multiway causal graph. When you show all those events explicitly, how they're related to each other, then you can talk about whether you can swap the order of A and B depending on how you're moving relative to them. So it's like a single history here is just generates a single space-time. But because there are multiple of them, those correspond to multiple possible histories.
Yeah.
The only difficulty here is just to make those history interfere with each other. And we already kind of came close to it, just having different signs and doing random works between them. It's kind of a very fun picture to imagine. Right? Yeah.
Do something like this. It's like a random walk, like you go here, 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 something like that. And it's
yeah, but only if those states are actually equal up to that sign, right? Because those your final vertices in this graph, you pretend that your E and D are actually the same state, but E may be positive and D may be negative. Then you can kind of walk between them. But if you ended up in negative, but you have to well, maybe with two states it doesn't work. You have to at least apply multiple experiment results. So there's effectively many branches ended up with different histories producing the same state, but with many possible sign permutations. Right? Then you can effectively do a very complicated random walk between them, depending how long is your histories. But there are going to be a lot of histories producing the same state up to the sign. And the point is that you have to additively jump at least 2 times, effectively annihilating them. Something like that.
Makes sense. All right, a couple more comments here, and then I think we can have a weekend to ponder the profundities that we encountered here today. Eames was saying, I believe Professor Wolfram posits that Eames are atoms of existence space. Then, if I recall, the physicalization of this is by using Planck units and applying some computational conjugate. I just remember the approximate elementary length was around 10 to the negative 90, 10 to the negative 100-ish meters. Yeah, the concept of Eames is interesting, and it's like, what is the most elementary unit of computation here? And kind of, if you switch around the concept of observer, or just think, like, the thing is, I don't think we can constructively say what an observer is yet. What we can say is that observations, you can only observe events, right? And every time something happens, every time there is a computational step taken or a computation takes place, this is an event that can be observed. So in my thinking about it is that observations are equivalent to events, and there has to be something to say about multiple observations. Like, an observer has to be something that you can identify, or that has some kind of persistent information engaging with multiple events, multiple observations, iteratively. Whether it's local or non-local, or whether it's a group of things, or a piece of information, a hypergraph, or a set of rules, whatever it is, I think that feels like all we can say right now. So Eames in that description of the world would be something like updating events, and that's about the most elementary thing you could say, is that these events occur and that these are Eames of existence. If you want to build it bigger than that, yeah, that might be difficult in the Ruliad.
Well, it's true that Eames are the most elementary ones. You can also think of them as computationally as just locations or memory addresses or references that you can just link together in order to form your space. That's why it's computationally a minimal element to even construct anything like potentially looking like space. Right? The next step, you try to describe how you do actually need those Eames together in order to form it. That's when the events come in and actually link and produce a bunch of causal links between those consequent events. Yeah. And the observer, yeah, well, we already tried to construct an elementary observer. It's just this minimal path through this sequence of events, maybe minimally containing some kind of clock in order to measure those intervals between events. But yeah, that's how you can minimally construct an observer from this constructive picture.
But could it be a rule? Like, if you have two observers
well, we just discussed it. It could be a rule, but just effectively, it's going to be just acting on some structure in there. All of made out of those Eames. So then you can assign more naturally the Eames in bulk to the observer. observer being this bulk of themes.
And then effective, if you use that in effective interpretation, wouldn't that allow observers to interact? Because how a rule updates the potential for where effectively a separate rule could apply depends on the update, depends on, like, if there's rule A and rule B. How rule A updates the state determines when rule B can be applied. So you could say that there's some type of interaction that takes place.
Well, yeah, that's how you can determine this causal link between events A and B, or applying rules A and B to create an event. If they act on the same EAM, then obviously there's some link between them, and they only can happen one after another. So that's how they form a time-like separation. And if they act on the different teams, then they are naturally space-like separated. If they act in some very complicated, ambiguous way, then they effectively create a branch, and then they're branch-like separated. And if those space-like never create the same state, they never merge, so that is effectively creates completely separate branches.
Some kind of event horizon potentially. My thinking is just that it kind of feels like you need a third observer that has ambiguous information as to the interactions between the first two observers that allows for this ambiguity and quasi-probabilities to exist. So this is sort of my elementary thinking in terms of like 3 dimensions. Like if every dimension is an elementary observer, you need at least 3 EAMs for quantum effects to start materialize, if you say that quantum effects are quasi-probabilities. Because from the perspective of observer C, which is now interacting with both A and B, there's certain interactions between A and B that observer C is not going to be privy to. So from the perspective of C, there are sort of some kind of equivalency or some kind of interactions that it has to have a reduced set of probabilities for.
Well, if anything, I think it's the other way around. So you can effectively have quantum effects using 2 observers, because what would be the quantum recounting of events in this kind of picture? Just one observer trying to describe the information about some system or state, or just describing how this information evolves, and then potentially measuring, and from his perspective, because some particular branch was chosen, the state collapsing, right? But for the third observer, there's no collapse, because he can observe all possible alternatives being without knowing what those the second observer actually observed. So he still preserves the evolution unitarily. So it's kind of no those conventional quantum effects happening from the point of view of the third observer. And as soon as like he asks a second observer, and you can still talk about the collapse happening and the particular branch chosen, but then for another observer, there's no branch again. There's no choice and collapse happening. It's just he exists in all branches, and you can just extend this argument indefinitely.
It seems like there has to be some kind of objective party to that. In other words, we who's seen the 2 interactions can observe that there is a collapse. If you're just one of those observers in that example, there's no collapse because there's no information of ambiguity with which you can pass on to an objective third party. That's just my feeling. It feels like we who have the zoomed out view of the whole structure is the third observer in that example, realizing that there's a collapse. From the objective of that elementary observer in the 2 observer system, there's no collapse happening because there was never a set of probabilities that could exist from its perspective. It's almost like too elementary for it to contain potential future outcomes. There's only interactions that it has. But that's just like a almost like a philosophical argument than it is a mathematical argument. There was just this nice explanation that I was reading Wigner's Friend. So the way Wigner explained quantum or the wave function is the wave function describes a set of future probable, like future outcomes, as it's a way to package up information of potential future outcomes that can be communicated to another person. So if there's another person that has the same observational ability as you, it's a way of describing future outcomes that the other person can then have a similar experience of. So it seems like part of this thing of being able to explain a wave function is like the ability to package up the information and have it communicated to somebody else. And that's what generates the information, is the ability to communicate it, whether it's human or not. I mean, that's like more philosophical here, is that, you know, we always assume that the observer is kind of anthropomorphic. It's like a human, like, or it's an experiment or something. But the third objective observer you could be interacting with is physical reality. It could just be the rest of everything else. Sure. It could be the experimental table. It could be the lab itself.
The environment. That's what decoherence essentially is, just interaction within an environment.
Exactly. So that's kind of the minimum required third objective observer. There's the thing you're experimenting, there's the experimenter, and then there's the environment. The environment is the third objective observer in that case.
Yeah. So it's besides the clock, an observer may have like this, require some ability to describe this informationally. All the observation he does, but not precisely.
Yeah.
It's like maybe a level of precision that one observer can achieve is also a part of its definition. Maybe that's a level of boundness we are talking about quantitatively. It's like how much he can describe, an observer can describe a state of system, even if it's probabilistically, even if it's like probabilistic, he still has to describe what his beliefs about its potential future outcomes.
That's a good point. I mean, that's actually, if we go back to your example, that's probably the clock in that experiment, and the clock has some kind of computational boundedness as well in terms of how accurate it can measure its updating steps. You know, like if the clock's hertz is 10 hertz, but the actual updating events are 1000 hertz, there's going to be some degree of, or like it's off by one, so it's like 1666 hertz or something. Then the accuracy of the clock is going to be computationally bounded, and the observer has to interact with the clock to get some kind of reading on what's happening with observer B. So there's some kind of interaction happening between that observer who's trying to keep the time steps. Yeah.
Yes. Yeah. The clock is all you need.
Actually, it's so funny. You know, like sometimes when you some weird memory gets triggered of something you haven't thought about in a very long time, and we were talking about like traveling through the different paths. I remember there was this series when I was growing up on TV called Time Travelers. Did you ever watch Time Travelers?
No.
It was the most cheesy, like low budget, funny. It's kind of like Power Rangers, but they don't fight. They just like travel through time and solve mysteries. It was so cool, and then you like go through these portals and stuff. And I was like,
I remember this other series called, I think it's called Sliders.
Sliders. Was it Sliders? Maybe. And they jump through the portals.
Yeah, they like have alternative universes. There's like
that's what it is.
Penicillin was never invented, or like an atomic bomb was never triggered.
I think that was it. Yeah, and it started getting weirder and weirder. I remember, like, I think the writers were struggling to come up with ideas.
I noticed. Yes, I remember that. I was so disappointed in the last season. It's like the dinosaurs, what aliens? I don't know. Brain in a jar. It was so stupid.
Yeah, was it called Sliders? I'm gonna have to YouTube that.
I think it was Sliders.
Some Time Sliders or something. Yeah, like.
Oh, I remember the Russian name. I was watching it dubbed, so I don't know. Yeah, Sliders.
Yeah, it was good. Oh, it's still on Fox. Okay.
Maybe first, second season was good. Yes.
Interesting.
Okay.
Yeah, so kind of like taking random walks through the possible paths of the causal multi-way graph feels like we're time sliders or something. Okay, I think that's good for a Friday afternoon. It was a nice mix of legitimate code and quasi probabilities based on legitimate theoretical frameworks, and a nice bit of profundity based on some retro narrative explanations. And, yeah, time sliding through the causal graph to try to come up with a way to philosophically understand observers. So yeah, nice mix there.
Yeah.
Cool. Okay. So yeah, we'll next week we've got the hypermetrics workshop. So that's very exciting. There's going to be a lot of very cool high level mathematics discussed there. Some really practical applications to ideas involving hypermatrices in general. That's kind of the general theme. But it's 3 days of very interesting, very highly qualified speakers that are going to be talking. So definitely tune in for that. And we will record those sessions as well, probably via live stream. So yeah, join us for that or watch them afterwards. It's going to be some really cool new ideas to think about going forward. So yeah, we hope everyone signs up and enjoys that live, so I can actually interact with the speakers too. That'll be cool. All right, Monday, Tuesday, Wednesday next week. Great. Okay, thanks for today. Thanks for everyone in chat joining the profundity, and we'll see you next week. Bye for now.